Okay. Okay, so today I'll tell you about entanglement groups, which is kind of our, I guess, attempt to get a better understanding of kind of really a fundamental question, but just to ask, what is entanglement? And certainly that's it's been kind of discussed extensively and thought about extensively, but I think we kind of felt we weren't satisfied with our perspective or our understanding, and wanted to understand it better. And this is kind of what we came up with. I guess I should say this is a paper from about a year ago. And then some more recent work in progress. So I think if you ask someone kind of what is entanglement, or how should we understand entanglement, I think there's a couple different answers that people might give you. So one possible answer, so a tensor product state is unentangled, and everything else is entangled. And there's nothing wrong with that definition, but I guess in some ways I don't find it very satisfactory, because after all, it's a negative definition. It's saying what entanglement isn't. And it's not really telling you what entanglement is. What kind of special properties or what kind of special features should entangled states have that kind of make them do whatever it is they do. So I don't like that so much because it's a negative definition.
Sorry, are you thinking of pure states of multi-party systems or bipartite?
Yeah. So for the first kind of the first part of the talk, it will all be on pure states, and bipartite is the simplest, but I'll also talk about multipartite states. And then towards the end, the work in progress, I'll say how this extends to density matrices. So that's kind of a negative definition. I'd like to say what entanglement is instead of what it isn't. I guess another thing that people kind of often say when they're talking about entanglement, the phrase always comes up that there's spooky action at a distance. So that is a nice phrase, I guess, especially when we're coming up on Halloween. But what does that mean? It's kind of a nice phrase or a nice slogan, but is there really some kind of precise mathematical meaning to that? So I guess I'll put a question mark there. I guess the third thing that I think if you'd asked me, this is probably what I would have told you before we started this work. If you start with consider a pure state, you look at the spectra of all of the reduced density matrices. You can certainly do that, start with your pure state, kind of trace out whatever you like, get a density matrix, look at the eigenvalues. Those spectra certainly give you a huge amount of information about the state. Um, they do kind of reflect the underlying entanglement. Now maybe this is a good way to characterize entanglement. But I guess the thing that I kind of don't like about this third perspective so much is that these reduced density matrices, they have statistical uncertainties. They tell you that if you do measurements on any subpart of the system, there are inevitably going to be statistical uncertainties. But those don't really seem like entanglement directly, as much as a consequence of entanglement. Again, this kind of third approach, I think I'd say it's more characterizing a consequence of entanglement than kind of entanglement itself. So we kind of wanted a kind of a sort of a more direct way of saying what entanglement is.
But the two is precise in the sense that you measure one operator and then the results of the other operator will depend on what you find in the first, I guess.
The spooky
Yeah, like you
action
measure
of the-
this operator and the probability distribution of the other depends on what result you got here.
Yeah, so our approach, I guess if you like, it's going to be giving kind of a precise mathematical meaning to number two.
So sorry, number three, even to characterize that set for all quantum states is an unsolved problem. Just forget about entanglement. It's a very hard question.
Yeah, yeah. So the kind of mathematical questions are going to be very difficult, kind of computationally very difficult. We're not going to get around any of that computational difficulty, but what I do hope will provide is sort of a framework that has kind of a clear interpretation, and then doing the hard computations is going to be someone else's. So this is kind of the one that I'll build on, and there's an old idea, and credit where credit is due. Schrodinger, I think in 1935, wrote a response to the EPR paper, and he didn't quite say it this way, but the approach is going to be to understand entanglement in terms of stabilizers. And yeah, if you look in Schrodinger's paper, somewhere in there, I think in a footnote, he has a stabilizer. So let me kind of say what the proposal is, and to illustrate the idea, I'll stick to kind of the simplest possibility, and I'll just talk about a pair of qubits to get started. So let's imagine that we have two spin-a-half particles. I'll call them A and B. We put those two particles in separate labs, so there's a lab A and a lab B. And then we imagine that the people working in these labs can apply whatever unitary transformation they like to their particular qubit. So, so we imagine that if we have some state for the combined AB system, that well, experimenter A, experimenter B can apply unitary transformations of the form UA tensor product with UB acting on the state. So I guess transformations, kind of factorized unitary transformations like that, I'll call those local unitary transformations. And then, you know, what can happen? There could be a local unitary transformation that leaves the state invariant. So suppose UA tensor UP acting on the state. Well, I guess it doesn't have to leave it invariant if it multiplies it by some phase, then that's as good as invariant for us. So that's a local unitary stabilizer. So those transformations form a group. But we won't want to consider kind of all of those transformations as non-trivial, because there are some things, some transformations which, for our purposes, kind of act trivially on the system. So there could be stabilizers. Maybe A does something to their system. B doesn't do anything at all. But if that's applied to the state, and you know, maybe it transforms the state by a phase, something like that, we regard as a trivial stabilizer. It's true, it's a transformation that leaves the state invariant up to a phase. But this was just something that A did by themselves. So you know, B didn't do anything at all. And so you know, we'll regard that as trivial. Or likewise, if A doesn't do anything to their spin, and B acts with some unitary. We'll also regard that as being trivial. So we'll want to kind of focus on kind of the non-trivial stabilizers, the ones that kind of don't have that form. And those have kind of a nice, kind of clear physical interpretation. The non-trivial stabilizers. You can think about them in kind of two different ways. One way you can think about them, well, you could say it's an operation that A performs. So that's something that A does to their qubit in their lab. But then B can undo it. So there's kind of a compensating transformation that B does to their qubit, which you know, kind of cancels out. The combination has no effect on the state. And that's kind of, well, Yeah, so that's spooky action at a distance. A does something in their lab. B could be, well spatially separated, does something in their lab that undoes what A has done.
But you're only restricting to unitary operations.
Yeah, that's right. You could, there are kind of various possible generalizations of this that you could imagine. You could imagine doing special linear transformations or something like that.
Well, a natural set of operations could be classical communication, meaning that they could coordinate their unitaries.
Yeah, that's right. So there are various kind of generalizations that of this kind of approach that I think are worth exploring. What I'm going to stick to is the idea that A and B apply unitary transformations. So, so you can think about these non-trivial stabilizers as something that A does and B can undo. Kind of rewriting that a little bit trivially. It also means that there's a transformation that A can do. Which has exactly the same effect as if A doesn't do anything and B does a transformation. So we need an inverse, so this sort of we're going to take these non-trivial stabilizers to characterize entanglement. And we think these properties kind of provide sort of an operational or kind of experimental meaning to this idea of spooky action at a distance. So that's going to be the kind of goal, to take states, identify these non-trivial stabilizers, and then work out what their consequences are. So that's the kind of framework that we're going to pursue. Like I say, any questions about the framework?
You could write that condition as a condition of the density matrix, right? Sort of like UA times rho half is rho half times U. Right.
Yeah. Let's see.
But this is the mirror. You're saying that the condition is that the mirror of UA is a unitary.
Yeah.
Yeah. Okay.
Yeah, that's right.
Yeah. Okay. Then it's yeah.
So I guess just to kind of make things a little bit more concrete, let's stick to the case of 2 qubits. Consider some possible states, and then ask what these stabilizers are. And yeah, pretty simple exercise. Yeah, I can do this in undergrad quantum mechanics. For a pair of spin 1/2 particles, there were kind of three cases. The first case is the starting point. We could consider a tensor product state. So both particles are spin up. And if you ask kind of what the stabilizers for this state are, well, there aren't any. A has to apply some transformation. they can't map the state 0 to anything else. It has to stay the state 0. So they could, I guess, multiply it by a phase, but that doesn't count as a non-trivial transformation. And the same for the state B, for qubit B. So the only stabilizer is just identity on A times identity on. And that fits kind of very well with the idea that this state is unentangled. I guess the other kind of possibility is a generic state. So if you want a generic state of 2 qubits, you could write it as cosine of some angle. Both particles spin up, plus sine of an angle, both particles spin down. And I guess the angle there is restricted. I guess generic means alpha goes from 0 up to pi over 4. So for that generic state of 2 qubits, now there is a non-trivial stabilizer. You can choose your unitary on A. It could multiply the spin-up state by some phase and multiply the spin-down state by the opposite phase. So that is some non-trivial transformation on qubit A. And then in order to leave the whole state invariant, the transformation on B has to be correlated. The phases kind of just need to be opposite. So that's a non-trivial transformation that A can do and that B can undo, basically by doing an opposite phase rotation. So that's a non-trivial stabilizer, and this forms a group. The group here is U1.
So this is just SU4 quotient and left and right by SU2.
Let's see.
Because all unitaries acting on 2 qubits is SU4. And you're quotienting it by unitaries on the left and unitaries on the right.
Let's see. Well, I want my unitaries to be tensor products.
Oh, you want tensor? Oh,
yeah,
that's right.
I'm always going to stick to tensor products. So, so yeah, this would be.
Oh, I see.
Yeah, so you start with U2 cross U2. And then, yeah, this is a U1 subgroup. Okay, so now we've picked up a stabilizer group, and it fits with the idea that this state is partially integrated. And then, well, the next step, we can look at a Bell state. So the Bell state, that one is maximally entangled. And now the stabilizer group gets bigger. If you ask for stabilizers, you've actually got a pretty large group. I can do U, let's see, I guess U tensor product with its complex conjugate. Acting on the Bell state leaves it invariant. Let's see, I guess, is that obvious? It's, I guess it'd be a little bit more obvious if I had a minus sign there and thought of the Bell state as being a spin singlet. Then it's annihilated by total angular momentum, and then I wouldn't need to put the star there. Then it would just be U tensor U leaves it invariant.
You started with transpose, I'm confused.
I think it's a star. I think it's a star.
Oh, maybe your definition was U A tensor identity acting on the state is identity tensor U B dagger.
Yeah.
Okay, then that's what it is. Okay.
So now we've got a larger group of stabilizers. U here can be any element of, well, let's see, I guess if I'm sloppy, I think I'd say SU2. I guess if I'm a little bit more careful, I don't want to include the minus the identity, because that's just multiplying the state by a phase. So I guess if I'm more careful, the group of non-trivial stabilizers is actually ESU2. So the mod out by the center, divide by Z. So this is kind of a simple but kind of prototype example of taking states, looking for stabilizers, and it kind of fits. The more entangled we make the state, the bigger the stabilizer group, the more things that A can do that B cannot do.
So intuitively is to measure how much we teleport.
Yeah, that's right. Yeah.
It's very, very pragmatic.
Uh,
Very pragmatic.
yeah, so I think if yeah, this was one of the things that we looked at. If you look at the protocol for teleportation, at some point you use a stabilizer. The fact that acting on one part of the system can do something to another part. So let's see, I guess the so this was kind of a simple kind of prototype example. For this example, you don't really need kind of much machinery. But there is a kind of a mathematical kind of structure kind of behind all of this. And so I guess I'll turn to that and give you some kind of general definitions of what we call entanglement loops. So let me start with a bipartite system. So my Hilbert space is going to be a tensor product HA tensor HB. And I imagine that I have some pure state in that Hilbert space. And yeah, I'll mention how this extends to density matrices a little bit later. If we're given a state like that, we can define local unitary stabilizers. So that's a group, I'll call the group SAB. And it's just the set of unitaries on A, tensor unitaries on B, such that, such that the state is invariant up to a phase. There's always kind of a wiggle caveat up to a phase. But then, kind of just as before, some of those stabilizers are kind of trivial in the sense that there's a group SA, which is just unitaries on A, tensor identity on B, that stabilize the state. And likewise, there's SE. That's identity on A, tensor, some unitary on B that stabilizes the state. So we want to consider these transformations, SA and SB, to sort of, we're going to regard them as trivial. But there's a kind of a nice mathematical structure here. So it's pretty easy to see that SA and SB are commuting their normal subgroups. Of SA. That's pretty easy to see. Clearly, SA and SB commute with each other. And if I take, say, a transformation in SA, and then if I conjugate it by an element of SAB, then what's going to happen? There's an identity on B there, but I have a UB from the left and a UB dagger from the right, so those cancel out. So it takes me back to an element of SA. So we've got these two commuting normal subgroups. And then what we can do is we can make the quotient group. So that's what the entanglement group is. The entanglement group for A and B is the stabilizer group SAB mod the trivial ones, SA plus SB. So that's what we call the AB entanglement. So I guess one nice thing, for bipartite systems, you probably don't need all of this machinery. This kind of seems a bit like overkill. Bipartite systems you can kind of study in more down-to-earth ways. But this does generalize to tripartite systems. Say how that goes. Tripartite system. So now our Hilbert space has three factors to it. And there are a bunch of groups we can define. So the first one, kind of the starting point, there's SABC. So that's stabilizers that have the form unitary on A, tensor unitary on B, tensor unitary on C.
Right, just one thing that's confusing me. Just in my head, I'm comparing with the conventional entanglement theory, and I'm confused about the following fact. So you're in conventional entanglement theory, we can say two states are in the same entanglement class. You don't have that notion, right?
So I guess I think we do in the sense that these groups we're building are invariant under local unitary transformations. So if I do a local unitary transformation on my state, I apply some unitary on each of the pieces, then under those transformations, the stabilizers get conjugated.
But your EAB is a map from the states to groups,
Yeah, that's right.
right? So. We'll discuss it later. Okay, good.
Yeah, that's right. I think
It's not quite clear to me how local unitary UA tensor identity will introduce a relation in language of maps that send states to groups, but
yeah, I think
it's not needed. Hang with you. I'm just trying to compare in my head.
Yeah, I think that this is kind of a I guess as far as I know, kind of a new feature here that in terms of trying to introduce sort of a measure for entanglement or a classification for entanglement. We are saying that entanglement is it's classified by groups. And for bipartite systems, there isn't too much structure to the groups. For multipartite, there's actually a pretty intricate mathematical structure, which we haven't been able to fully understand. But I can kind of set it up and then kind of tell you some of the properties.
So sorry, just to understand. So for bipartite your states, the outcomes of the group are either trivial identity or U1 or PSU2. Those are the only possibilities, right?
For bipartite pair of qubits, yeah.
I see. And then that explodes as you put the higher partite.
Yeah, and I guess for multipartite, the groups have kind of an intricate sort of a tree-like structure. And yeah, there is a kind of a much more an intricate mathematical structure.
But maybe you said that the trivial ones are the UA 1, and like that, or what's the trivial?
Yeah, good, exactly. So this would be our group of stabilizers, but then we do want to view some of them as kind of trivial. So SA would be yeah, just as you say, UA tensor 1, tensor 1. It stabilizes the state. Similar for SB, similar for SC. And then we define, or you can define what we call the full entanglement group. And that's kind of the direct extension to the tripartite system. You look at your stabilizers, UA tensor, UB tensor, UC. And then you mod out by, well, now there were 3 commuting normal subgroups. So you mod out by the trivial ones. That's the full entanglement group. We'll call that FABC. But there's quite a bit of structure to the full entanglement group. And the reason is that we've got a whole bunch of subgroups. Even though we've got a tripartite system, we could define what I'll call SAB. So those are transformations UA tensor UB identity on C that stabilize. So those are kind of, those are stabilizers that only act on the first 2 systems. And then what I could do, I could still define EAB to be the stabilizers that act on the AB system log SA cross SB. So that's a group that captures kind of 2-party entanglement. Just between A and B. And likewise, I can define groups EAC, EBC that capture the entanglement between any 2 the systems that I like. It's not too hard to check that these 2-party groups are actually normal subgroups of the full 3-party group. For kind of the same reason that a 2-party stabilizer would be a normal subgroup of a 3-party stabilizer. So that means there's actually a further quotient we can take. So this is what I'll call true kind of 3-party entanglement. So that's a group EABC. And the way you make that, you take the group that has kind of all of the entanglement in the state, FABC, and then you mod out by these 2-party entanglement groups. So you mod out by EAB times EAC times EBC.
So is that the same thing as SABC modded out by SAB, SBC, SAC?
Yeah, it is. There's a, let's see, yeah, Noether's theorem, but she did math theorems as well as physics theorems. That's the same as doing the quotient of the 3-party stabilizer by the 2 parties.
So the quotient n part-type unitaries by n minus 1 part-type unitaries.
Yeah, that's right.
Is this dot different from this cross? Like it?
Yeah, it is. SA and SB were commuting subgroups. So this is actually a direct product. SA and SB don't have any elements in common aside from the identity. Um, these groups are all normal subgroups. And the dot there is just a group product. So you take all of the elements of these different groups and multiply them together. It turns out that gives you another normal subgroup, so you can still do the quotient. But it's but these different groups can have some elements in common. I guess it's clear that they do, because if you looked at a stabilizer that only acted on system A and didn't touch anything else, that would be in both SAB and SAC. So yeah, that's kind of minor math detail.
And these groups, do they ever end up being discrete?
Yeah, they can be discrete.
Sorry, I don't mean to interrupt.
Yeah, I think maybe.
Yeah.
Let me give you an example.
But for GHZ, that group that defines the U one, or is it discrete?
Yeah, so good. So I guess for a three-party entangled state, GHZ is kind of the prototype. The state is it's sort of a three-party version of the null state. And let's kind of look for the stabilizers and kind of say what the entanglement groups are in this case. And I think it's pretty easy to kind of figure out what they are. So the GHZ state, there is a group EAB. So those are transformations that just act on spins A and B. And it's basically the same as, let's see. So I do kind of equal and opposite phase transformations for spin up and spin down on system A. And then I compensate by doing the opposite phases on system B. And then I don't touch systems. So that's a transformation that kind of leaves GHZ invariant, only acts on A and B. It's a non-trivial transformation. So we have a U1 group of a U1 entanglement group between A and B. And then I guess things are pretty symmetric here. So EAC is also a U1. EBC is also a U1. Those are the two-party transformations we can apply. But then you could look for a three-party transformation, so something that acts non-trivially on all of the spins. That would be the group EABC. And that one is a Z2. So of course, it has the identity as an element. And then the other transformation is XA tensor XB tensor XC. X there is the first polymatrix. It just flips spin up to spin down. So what does that do acting on the GHZ state? It just exchanges the two terms. So we have a U1 two-party entanglement groups and a Z2 three-party entanglement.
So you don't have to work that, but like, what's it for W3?
Let's see,
That's
so
that's the only other state I need to know, right?
for W, yeah, what is it for W? For W, there's no two-party entanglement. The three-party entanglement is a U1.
Oh, it's U1.
Yeah.
Wow,
Um,
so the group is larger for W than GHC.
What is W?
Oh.
Excuse me.
yeah, I can write that down.
It's a sequence. 0, 0, 1 plus 1, 0, 1, 0 plus 1, 0, 0.
Yeah, so there's also the W state, which is what you just said. Great. That's right.
I don't know. What I remember is cyclic symmetry. But that might be, I don't know.
Okay, let's see.
That doesn't matter. The reason I ask is that usually W and GHC stand out in tripartite entanglement theory.
Yeah, so I think for this state, EAB, EBC, and EAC are trivial.
If for the first thing you interchange 0 and 1, you get what Nima said, right? Because you get
Yeah.
1, 0, 0, 0, 0, 1, 0, 1.
Yeah, maybe that's a better way to write it.
Now it's sort of set here.
But for this, EABC is a U1. So, yeah, the groups have kind of an intricate structure. They fit together in kind of a complicated way. And I guess kind of as a mathematical, I don't know if this is a mathematical curiosity, but like for GHZ, you can you could talk about the full entanglement group that includes both the two-party and three-party entanglement. And you could ask, what's the structure of that group? Well, it's kind of built up out of two-party and three-party entanglement, but kind of how exactly? I guess one thing, in GHZ, these three groups aren't independent from each other, because if I do a transformation on AB, and then I do a transformation on AC with the opposite phases, then I'll be left with identity on A. So that means there's an element of EAB times an element of EAC that gives me an element of EBC. So actually, the way the full three-party and the full entanglement group is built up, it's got two U1s in it from two-party entanglement. And it's also got three-party entanglement. And kind of the math structure there is it's a slightly product. I don't know if it's always like that, or like there is kind of an interesting, I think, math structure to the way that these entanglement groups for states kind of. You can define a full multi-party entanglement group, and then it splits up in sort of a. Kind of a, it's sort of a tree-like structure where it has all of these subgroups corresponding. The n-party entanglement group has subgroups corresponding to n-1 party entanglement. Those can have subgroups corresponding to n-2 party entanglement. So there's a whole kind of structure there, which would be nice to unravel.
I have a question that if we're thinking the like stabilizer code, like a quantum state is represented by the uniquely by the stabilizer group, which is similar here, but we request that all the measurements for the eigenvalue is +1, for example. And that EABC, the only non-trivial term, is actually the only non-trivial term inside that stabilizer group. Like, I mean, for example, your state here, 0, 0, 0 plus 1, 1, 1, the stabilizer group for in that language is ZZ1, 1ZZ, and XXX. And that is only like the three-body operator appear in that stabilizer group, and it appear also here. So
Yeah.
I'm thinking, are they kind of relevant here? Like also here for the EAB, each of them is actually somehow like exponential of z, right? The first is exponential theta z, and the second one is exponential minus theta z. And somehow the ZZ one is also the stabilizer inside the stabilizer group in that language. So I think they are kind of
Yeah, I think there should be, there should be a
I have
connection.
one confusion regarding this. In stabilizers, we are talking about abelian subgroups.
yes.
None of these structures is necessarily abelian, right? But non-abelian things come up. In examples, yes, maybe.
Yeah, it'd be interesting to explore.
Yes, I think the question is, yeah, I mean, the stabilizer defined here is stabilize the states up to a complex phase or is a complex phase. So it won't be matrix. So I think it should be somehow still abelian somehow, right? But like, I think that phase kind of make something here happens. Like it is not directly the operators in that stabilizer.
Okay, yeah, I'm sure that would be interesting to explore a connection there. Let's see, I guess. It's, yeah, I guess maybe the kind of last, well, let's see, should I, yeah, no, I guess how are we doing on time? We should.
We have time if people have to leave and have to miss it, but you started late and please feel free to continue. How much time would you like?
All right, well, maybe I'll just mention a little bit about density matrices and how this extends to density matrices.
My trivial question, as you said, with the two spins, because I have an even number of spins, I always have a spin zero state. That is invariant under SU2. But I don't know if that total rotation is trivial in this way or not. So it's always SU2 stabilizer then.
Let's see. Yeah, I guess that would be. Yeah, so that the state that's invariant under SU2 would be a particular state that of those n spins that does have n-party entanglement. Yeah, that's right. So yeah, maybe I'll just kind of mention how this works for density matrices. So for a density matrix, our starting point, we have some density matrix rho AB. And it's some on a bunch of probabilities, some state of the AB system. That's our kind of generic density matrix. And one thing we can always do is we can purify. So we can write down a pure state, which is built out of the same states for the AB system. And then I introduce some auxiliary purifying system C. And I want my states for the auxiliary system to be orthonormal. And then it's clear that you build the density matrix out of this, trace out system C. It gives you what you want. And there's freedom in choosing a purification, but there's not too much freedom. The purification is unique up to unitary transformations on system C. And so then the kind of question is, in this setting, is there kind of a useful definition of entanglement in terms of groups? And here's the proposal. We're going to introduce a notion of a stabilizer. So a stabilizer is going to be the transformation UA tensor UV that if I conjugate my density matrix, that it leaves the density matrix invariant. That's a proposal for defining the two-party stabilizer group. And then, well, that's for the density matrix. You can ask what it means for the purification. And so if we apply UA tensor UB, I guess tensor identity on C, if we apply that to our purification, it left the density matrix invariant. It doesn't need to leave the purification invariant. But since the density matrix is invariant, the most it can do to the purification is apply a UC transformation. That's the sort of freedom you have to go to some other state that would give you the same density matrix. But that's basically the same as saying that it's a, if you like, with this definition, the stabilizer for our density matrix is what we called earlier SABC for the purification. So that's the notion of a stabilizer for a density matrix. We can also introduce the kind of trivial stabilizers. So something that just acts on A and leaves the density matrix invariant. That lifts to a stabilizer that before we called SAC for the purification. And SB for the density matrix. Those would be stabilizers SPC for the purification. And then we can kind of set up exactly the same machinery. We can define an entanglement group for our density matrix. It's the stabilizer group, mod SA plus SE. Or, and that's in terms of the density matrix. If you want to think about it in terms of the purification, it would be the three-party stabilizer, including the purifying system. We're dividing by something a little bit different than what we divided by before, because now we're dividing by SAC plus SBC. For example, I guess, yeah, that actually be a good product. So that's how the kind of scheme extends to density matrices. And kind of the idea is that we're still thinking about it in terms of stabilizers. You can think about it in terms of a stabilizer for the purification, except that for your stabilizers, since you don't have access to the auxiliary system C, you don't know what kind of transformation somebody might be applying to system C. So you always include system C in the groups that you're building the quotient. So yeah, I guess that's that covers everything. Yeah, happy to answer any questions.
At the start, you discussed an example where you basically showed that the more entangled the state was, the larger group it had. So it's a stabilizing group. Does that hold in general, or is it just for a particular example?
So yeah, it holds for that particular example. It's a little bit, yeah, I'm not sure if there's a useful sense in which it kind of holds in general or holds for kind of multipartite entanglement. And kind of I guess the kind of stumbling block, and maybe there's some good way to think about this that we kind of haven't come up with, but for multi-party entanglement, you get this kind of structure of groups where there's all this kind of a tree-like structure of groups and subgroups. And I don't know if there's really a meaningful way to look at two groups like that and say that one is larger than the other, or smaller than the other. I don't know if there's a kind of a good notion like that. Yeah, I don't know if there's kind of a meaningful way to do a comparison of the groups in general.
Yeah, maybe related to that, but is there like any known relation to entanglement monotones of any kind? Like, like you can't say directly compare, like you said, but could you say if the group is trivial, that implies that the entanglement monotone is minimized or something?
Good question. Yeah, I don't know the answer to that. Yeah, that is an appealing idea. But yeah, I don't know the answer.
Sorry, I missed that. So when you looked at Belpaire, what was the entanglement for Belpaire?
It was SU2, or I guess strictly PSU2, but yeah.
PSU2. The reason I'm asking is that when you wrote the W, you put generic ABC. I was wondering if I fine tune A and B and C, I would imagine I could change the E. There would be enhanced symmetries of different type of theorem, right?
Yeah.
So this.
Yeah. Check my. Um, let's see. It is.
So if I take the bell pair and I just put, instead of square root half, I put alphas. Actually, you did that example.
Yeah, then
That
it becomes
becomes
U1.
U1.
Then it becomes
So
U1.
then it's not, I mean, it's expected that it's not a continuous map. If there you have a state with some group, there's a state arbitrarily close to it
Yeah,
with a different group. Because the lead groups we're talking, or the groups we're talking about are not labeled, but are not continuous.
that's
There's
right.
no way of continuously defining it.
Yeah, that's right. And I guess, yeah, and maybe I should mention, so, that might make you worried because, you know, the Bell state has, this PSU2 stabilizer, but if I perturb the Bell state by epsilon amount, then it's not PSU2 anymore, it's a U1. And it might make you worried that things are kind of so sensitive to perturbations of the state. And so I think the kind of response to that is that the states that have kind of enhanced stabilizers, those are special states. And then kind of what's sort of physically relevant, if you have some physical system that has some state, what's kind of relevant is how close you are to one of these special states. It's a little bit like being, you know, kind of close to a critical point in condensed matter. So even though the enhanced stabilizer only, strictly speaking, is there for a very special state, if you're nearby, then it has.
I'm not personally worried. There are versions of entanglement theory that have that property, and there are versions that do not.
Yeah,
Does that continue?
this one does, I think. Is there another?
My question was actually exactly the same as Eva. I was curious about this cosine alpha 0, 0 plus sine alpha 1, 1. What was the range of allowed alpha? 0, larger than 0, smaller than?
I think up to pi over 4.
Four.
Once you get to pi over 4, then it's
That's
the
the
Bell
key.
state.
And when alpha is 0, it also changes to trivial.
Yeah, so it's tensor product when alpha is 0, and then yeah, base with 2 qubits kind of have 0 on one end with the tensor product. And then at pi over 4, you have the Bell state.
So it's U1 in the middle. It doesn't distinguish among those states in the middle.
Yeah, that's right. At the tensor product state, the entanglement group is just the identity. Generically, it's U1, and for Bell, it gets, well, PSU2.
I was wondering, so initially there was like 3 generic definitions of how we can think of entanglement, and one was related to the density matrix. And kind of common measure in terms of density matrix is like Born-Neumann entropy, or associated with the density matrix itself. Now, the way that I would imagine is in that Born-Neumann entropy, the eigenvalues are important, right? So this U tensor U, in that case for rho AB, it's like a unitary transformation, it's especially unitary transformation, it's just a tensor product, right? So in some sense, it doesn't change the eigenvalues and won't change the entropy itself. Obviously, it's equality. But even if I have some generic U that acts on this AB space, combined space, it still wouldn't change the entanglement or non-entanglement for that rho AB. So I was wondering, like, I would think that somehow all these unitaries that don't change that entanglement entropy might be associated with some group of unitaries that could characterize somehow the entanglement, but we look at very kind of special subgroup of that. So is there like a particular reason? Maybe I missed something. I don't know. Is that kind of to relate to the kind of definition of and standard definition, I would say, of the entanglement entropy itself. So we are just looking at just very kind of particular class of unitaries on AB.
Yeah, so
Just to reiterate, I see more like connection with the second definition of the spooky action, like how this relates to that, but kind of have a hard time relating to like entanglement, kind of defining like entanglement in terms of some entanglement measure, the complement entropy, and relating to this unitary structure. How would they kind of correlate in some sense?
Right, so, uh, yeah, so, as here, I have a density matrix for the AB system. And, I'm interested in, kind of entanglement between A and B. So I restrict to these, tensor product unitary transformations. I guess I could ask a different question, which is kind of not entanglement between A and B, but I could ask how the combined AB system is entangled with the purifying system. And then I could consider generic unitaries. I wouldn't need to restrict to tensor products. So the reason for the restriction was because I want to know how I'm trying to characterize entanglement between A and B.
Actually, a related question, there is, I don't know what name it goes with, but in the quantum info community, there is something that people call the LU invariant entanglement theory or local unitary entanglement theory. I don't know what the name is, but what it is a resource theory built on local unitaries, no classical communication, very similar to what you're set up. But I wonder, like, yeah, do you know if there are connections? It seems very natural that it's connected.
Yeah, so I think I would say that this is kind of an LU scheme for classifying entanglement. That the scheme is invariant under local unitary transformations without any classical communication.
That's the same philosophy over there too.
Yeah,
And that hence the comment that I had at the beginning. Over there, the important group is SU4 modded left and right by SU2s. You look at UABs modded by UA tensor UBs.
yeah. So at that stage, we're different because
Yeah,
I'm
it's very
starting from
different. Yeah,
tensor
for sure.
products.
No, for sure.
Yeah.
It would be interesting to see if there are connections. There might well be.
Yeah.
Right? The composition of unitary groups.
Yeah, there could well be. It's interesting to explore that.
What would we do if we want to apply this idea to identical particles? For example, if we want to look at fermionic state space.
Yeah, so we haven't really explored that. For us, the different qubits were distinguishable, but I would kind of imagine it wouldn't be too hard to extend to fermions or bosons. And I think what it would mean is you just have to take kind of an additional quotient by a permutation group. That's what I would expect.
Just to help my intuition, like when you had the middle state, so you had the SU2 or the PSU2 as the stabilizer group, like, but when you added one more particle, like kind of the two-part group was smaller. How did it happen? Like, that-
Yeah. So yeah, so if you have the Bell state, then there are SU2 transformations you can do to the first spin that you could undo acting on the second spin. If you have, say, the GHC state, then let's see.
Not 110 is not 001. So for the bells there you can swap 00 and 11.
But in the GHC, that is, you cannot swap a 0 and the first two 0 to 1 1. Because that's the third qubit that distinguished them.
Oh.
So the qubit size is smaller.
Yeah,
Yeah, that's right.
Okay.
yeah, so the only thing you can do here is kind of phase rotations.
All right, are there any last questions? There are a lot of questions.
Maybe one
Yeah, go
small thing, yeah, sorry. But when you were trying to capture the genuine tripartite entanglement, you modded by like identity tensored U B tensored U C, something like that, right? But we should also, I think, mod by identity tensored some U on BC, because I think with higher multipartite entanglement, that would not be the same.
Oh,
Because if you're entangling two things, that's not like a genuine tripartite.
yeah, so, I guess.
Yeah, sorry.
So, when we defined EABC to be, the full entanglement group mod EAB, EAC, EBC. So this is the three-party entanglement group, kind of relative to the division into three separate systems, A, B, and C. So have to imagine three different labs, A, B, and C, and they can each do their own unitary transformations. If you're just given the state, though, there are other things that you could imagine. So, maybe A stays in their lab by themselves, but maybe B and C, I don't know, form a collaboration and they can apply kind of combined unitary transformations on their system. And so then you could define, just in terms of the state, you could also look at how A is entangled with the combined BC system. And you can define groups for that as well. You look at the stabilizer where it's a unitary on A, tensor product with a unitary on the combined BC system, and then quotient. So you can think about kind of merging systems together and doing combined unitary transformations.
I guess he's like asking in the first definition for EABC with BC not combined, how do we also need to like mod out SBC?
With the combined.
Yeah.
Let's see, I guess. Yeah, I don't think I want to do that because whatever I quotient by better be a subgroup of what's upstairs. So
Yeah.
All right, let's thank Danny. Danny's here only today and he's sitting in 228, I believe. So. Thank you so much, everyone. Thanks so much.
So what I was kind of, this is really not, but it gives you different change for, right? So even if it's like this in general, unitary, but it's not a tensor product. So we have like a tripartite system, there's a 9, and then we trace out that, and then we have OAP. So, and really, that's not tensor. The field unitary, the unitary dagger would be meaning the same, but not what I was saying is like to relate to the entropy, I would think like somehow to relate to the all unitaries in the sense that even if I apply some generic unitary, it will change the OAB, but it wouldn't change the entanglement. So, but it's like a subgroup of that or subset of that, at least, subgroup as well. And so that's what puzzle me in the sense that so like in my work I'm using just OABs and then one nominator and so on. So I was like wondering how maybe how could I relate this structure to this third statement that you made initially? So is there like any maybe
If you look at the von Neumann entropy of low AV, so that is kind of characterizing the entanglement between the combined AV system and the environment. And so if you did something more general, if you had a unitary combined system. That would be with von Neumann entropy. So it's preserving the entanglement, the amount of entanglement between the AV system and the environment. But these kind of general unitaries, kind of move entanglement back and forth between A and the environment and B.
Yeah, so it's if you apply some generic unitary on row A, B, it pretty much is effectively like a one channel A and B separate. So it changes